Hi, good morning. Today we are going to talk about characterization of compact metric spaces. Most often in metric space, one usually goes through very quickly, perhaps for analysis on Rn, and sometimes as a prelude to functional analysis, and concentrate more on topology, the so-called general topology. There, the definition of compactness is in terms of open sets, and you deal with it frequently there. But when it comes to analysis, especially functional analysis and other parts, mostly it's metric spaces which are in play. So the characterization of compact metric spaces or compact subsets in a metric spaces are very, very important, and they are more useful than open covering. Okay, definition using open cover. So many students, especially when they go to, let us say, functional analysis, compact operators, etc., they have difficulty. Okay, so we plan to show 4 equivalent conditions and prove their equivalence. And I will also at the end, if time permits, I will explain which two of them are most important, especially for works with the analysis, differential equations, etc. Mostly analysis related subjects. Okay, right. Join me for this wonderful journey. Okay, so let us quickly recall some of the definitions which are needed for the thing. So X, I will stick to metric space. Okay, so when do I say it's compact? I have a collection UI. I vary giving some indexing set. UIs are open, and I say it's an open cover if X is equal to union of UI, I in I. That means give me any X in X, there is an I in the indexing set so that X belong to UI. That's what you mean by X equal to union UI. Okay, right. I say a subset K of X is compact if whenever you give an open cover UI I in I, okay, of possibly X, okay, there exists a finite subset. See, I am not writing I1, I2, IN, etc. I'll simply say it's a finite subset of the indexing set so that my K is a subset of union I in the finite set UI. If you are uncomfortable, this may be I1 to IN, which is a finite subset of I. That means J equal to 1 to N. That is K is contained in J equal to 1 to N. But it will, if you are going to be in higher mathematics, it's better to use this kind of notation and avoid this. Okay, but each has its own thing, so let me not worry about. Next, when do I say a metric space X is complete? If every Quotient sequence is convergent in X is convergent. Okay, so the same thing if if K is a subset of X, then when do I say K is complete? Look at the metric space KD, this is complete. What does that mean? Give me a sequence Xn, which is Cauchy in K, and then Xn converges to X. But this X must be in K, because remember it convergent meaning it should converge in that set. This is KD. Okay, and third, a subset A of a metric space is totally bounded. Okay, okay, for every epsilon positive, okay, there exists a finite subset F of X. Notice that A is a subset of X. This F need not be a subset of A. It may be a subset of X. So that my A is a subset of B X epsilon where x is in f. Okay. Then such an f is called an epsilon net for a. Okay. This, I'm sure when you come to this, you had already seen these things, but to keep the notations clear, I'm just recalling. See, this notion of total boundedness is a backdoor entry of compactness. Because suppose A is compact, and for every epsilon, I have Bx epsilon as x varies over x. This is an open cover for x, and here is an open cover for A. Therefore, I should be able to find a finite subcover. That's all it says. You understand that? Therefore, total boundedness is in some sense backdoor entry. Okay, the fourth concept is again in a metric space. Okay, suppose A is a subset of X. I say a point X in capital X is a cluster point or an accumulation point of A if for every R positive Bx R intersection A is not empty. This stands for deleted neighborhood of X. That means from the open ball you remove the center. So each Bx, that is Bxr intersection A, contains a point other than X, right? So you may know a different name for this cluster point accumulation point, but I don't want to say that because I'm not favor of calling these points by that name. Okay. Now what is the theorem we want to prove? Theorem we want to prove XD a metric space. Notice that this is, even though it talks about metric space, it may be characterization of compact subsets which are compact subsets, because when I say x is k is compact subset of x, it is same as saying the metric space kd is compact. You understand that? Okay, so there is no need for that. So let x be a metric space, then the following are equivalent. One, x is compact. This is the your standard definition using open cover. Two, every infinite subset u of x, okay, or let us say for every, okay, there exists x in x, so that x is a cluster point of E. You may wonder, usually one says every infinite subset has a cluster point, but when you say E has a cluster point, because of the English language, you may say the cluster point must be a member of E. That may not be the case. Do you understand that? So this loosely people say every infinite set has a cluster point. Okay, but the word has also has the meaning possess. That means the infinite set, the cluster point must be a member of the set. That need not be the case. That is why I formulate it carefully. How do I write it? For each infinite set, I can find an x which is going to be a cluster point of E. So I'm not pretending or claiming x must be an element of E. You understand that? So I'm making it careful statement. Okay, the third is every sequence has a convergent subsequence. Okay, and fourth, okay, every sequence in x, of course, because x has to be there, right? Okay, the fourth one is x is totally bounded and complete. Okay, are the statements clear? X is compact, every infinite set has a cluster point. I will just loosely say that, and every element in x has a every sequence in x has a convergent subsequence. and X must be totally bounded and complete. So the way we want to prove is cyclically. 1 implies 2, 2 implies 3, 3 implies 4, and 4 implies 1. So that they are equivalent. Okay, let's go back to the first page. See here I had given three references. The proofs in each of these three are different from each other. The way they are different is for the following reason. Okay, is for the following reason that the way 1, 2, 3, 4, these four conditions are written in order, they are different. Okay, that's the reason why they are. And very surprisingly, I found this proof which I'm going to give was something which I found out about 25 years ago, and that is in article number 2. So if you want to follow this proof, yeah, from a written article, then 2 will be closest to what I'm going to do. Okay, but it may be worth learning proofs in 1 and 3 also, and 2 and 3 will have lot of similarities. Okay, now let's start with the proof. 1 implies 2. What is 1? Compact. I want to say every infinite set has a cluster point. Okay, let E be infinite subset of X. Okay, then I want to say it has a cluster point. Suppose false. What does it mean? You give me any X in X, then X is not a cluster point of E. What does it mean to say X is not a cluster point of E? That means there exists an R, yeah, okay, that R may depend upon X, the radius, so that Bx Rx intersection E has at most X. You understand that? This is empty. That means Bx Rx intersection E is a subset of singleton X. It may be equal to or it may be proper subset. You understand that? Because if it's a cluster point, then for every R, Bx Rx intersection E must have a point other than X. All right. So if you say it's not a cluster point, then there is at least one R so that this happens, right? But X may be included. If I include, then that I am adding only one more point. Therefore, this will be a subset of X. Are you following? Okay, right. You may don't say this equal to because you look at open world 0, 1 kind of thing. If I 1, if I look at this, okay, let's not worry about. I'll leave it. Is that clear? Okay. Now I have found that means, so I have found this collection Bx Rx as X varies over capital X. What can you say about this collection? Notice that for each X, Rx is such that Bx Rx intersection E is B dash X Rx intersection E is empty, right? Okay. Now X belong to Bx Rx. Therefore, this is an open cover of X. But X is compact. Therefore, what do I know? I know there exists a finite subset with what property? My X is equal to Bx Rx as X varies over F because of compactness. Okay. Now, do you say contradiction? Let us keep it. Now, what is E? E is an infinite set, but E is same as E intersection X, right? But what is E intersection X? E intersection union of BXRX as X varies over F. But this is union of E intersection BXRX and X varies over F. Okay. But what is this? I know this is at most, this is a subset of X, singleton X. Therefore, this is equal to union of not containing, sorry, singleton X as X varies over F, but that is same as F. Are you following what I have shown then? The set E is a subset of F. But what do we know about E? It is an infinite set. What do I know about F? It's a finite set. That's a contradiction. So what does this contradiction show? It shows that my assumption, there exists no X in X, which is a cluster point of E. That assumption is false. That means if E is an infinite set subset of X, there is an X in X, which is a cluster point of E. Okay. So pause, review, and proceed. Take a few minutes, go through the proof, then come back. Now I want to say 2 implies 3. What is 2? Every infinite set subset of E, subset E of X as a cluster point, and 3 says every sequence in X as a convergent subsequence. So let Xn be a sequence. In where? In X. Right? Now I want to make use of the hypothesis. The hypothesis deals with the infinite set. Right? So I have to get a subset of E and preferably an infinite subset of E so that I can make use of the hypothesis. How will I do that? Let's look at the range of the sequence. Range of the sequence by definition is collect all nth terms as n varies over S. This is a subset of X. You understand that? Whereas Xn is not a subset. Xn is a function from natural numbers to X, whereas this is a subset of X. If sequence is natural number to X, then this is X of n. You understand that? Okay. Right. So now there are two possibilities. Suppose this range, okay, let us call this as E. Okay. Suppose E is finite or E is infinite. Let us call it A and B. Okay. Suppose E is finite. What does that mean? That means there exists one term which is okay infinitely many times, which occurs many times. If you want, if I can write it as, let us say alpha 1 to alpha k. All right, this is a finite set alpha k. Right. Then let us look at the set of all n in n, so that xn equal to alpha I. Okay. 1 less than equal to n less than equal to k. You understand this? Right. Now call this set as ei. Okay. Now what do I know about this? Set of natural numbers n is union of ei. Because every natural number has to this property. Because xn must be one of the alpha 1, alpha 2, alpha k. Therefore each n belong to this, and this is a disjoint union. Because because alpha 1, alpha k are all distinct. Right? Therefore xn cannot be alpha I as well as alpha j for I not equal to j. Therefore this is a disjoint union. And this is an infinite set. Therefore what do I get? Therefore at least one ei must be infinite. At least one. There is I said that ei must be infinite. What does that mean? That means look at the set ei. Then this is a subset of natural numbers, right? So I can write it as n1 less than n2 less than nr, etc. Right? Because E is infinite subset of n, therefore let n1 be the least element of ei. Right? Then from ei remove n1. This is again an infinite set. Therefore, by well-ordered principle, there is an n2 which is the least element of this. That n2 will be greater than n1 and so on. So this ei, the infinite subset of natural numbers, can be written as n1 less than n2 less than nk, etc. Do you follow that? Therefore, what do I have? I have xn r for every r equal to alpha I. Now, this sequence xn r is a subsequence, and it is convergent because it's a constant sequence. Therefore, xn r converges to alpha I, right? So, if when the case E is finite, that is the range of the sequence is finite, I have shown that there exists a convergent subsequence. Okay, pause, review, proceed. The next case is the range is infinite. Right? Now this is an infinite set. Therefore, there exists an x. By hypothesis, there is an x, x, and x, as that x is a cluster point. of E. Is that clear? Right. So what does that mean? Okay, that means there is a sequence. Okay, call it yk, a sequence in E, so that yk converges to x. Okay, that therefore this is going to be a subsequence in. You follow that? Again, if you are not, if your real analysis is not good, if you have not been careful with this kind of thing, okay, you may be slightly put off. You should learn how to do this kind of thing. Okay, so let us look at bx1. This intersection E, okay, has a point other than x, right? Call it as, but what is E? E is subset of xn's, right? As n varies over n. Therefore, call this as xn1. This is there. You understand this? Okay. Next, let us look at bx half intersection E. Notice that since x is a cluster point, is with any open ball, okay, x is a cluster point, then bxr intersection E, this is x, these are, okay, will have infinitely many, will be infinite. Okay. I hope all of you know that. If you don't know that, we will get, okay, come through a proof soon. Okay. Therefore, this is infinite. It is infinite subset of E, but E consists of terms of the sequence. Therefore, there is at least one n2 which is greater than n1, so that xn2 is here. Right? Okay, next I'll prove Bx 1 by 3 intersection E. Again, for the same reason, this is an infinite set of terms from the sequence. Therefore, there is an n3 which is greater than n2, so that xn3 is lies here. You understand? Therefore, I construct a sequence xnr. Okay, so that what happens? xnr lies in bx 1 by r. That means distance between x and r and x is less than 1 by r. What does that mean? X and r converges to x. Okay, so what I have shown now? I have shown that if the range of the sequence is infinite, then I can extract a convergent subsequence. Okay, how did I get the convergent subsequence? Yeah, if x is a cluster point of the set E, then we know there is a sequence which of E which converges to x, but we have to carefully choose a sequence as a subsequence. Okay, that's what the proof is about. Okay, now let's quickly go through this. Okay, this pink star, what does it pink star say? So if x is a cluster point, nothing to do with E, this is for any general case. If x is a cluster point of E, okay, then bxr intersection E will be infinite. If not, otherwise what will happen? There may be only, now I will write only finite minute terms so that it will be easier for us. Okay, I can do that without that anyway. Okay, suppose this is equal to finite set. Then, and I will also assume none of the x1, x2, xn are equal to x. X may also be a point. In that case, you remove that. Are you following? Bxr intersection E will be a finite set, but x may be a point of bx. Of course, it's a point of bxr. It may also be a point of E. So I remove that. Okay. Uh, Okay. Now this is the clear. This will be easier, right? Now let us look at the distance between x and xi for 1 less than equal to I less than equal to n. These are all positive. Therefore, if I take epsilon equal to minimum of d of x with xi 1 less than or equal to I less than equal to n, okay, then let's look at bx epsilon. This is a subset of bxr, right? And what do I know about bx epsilon intersection E? This must be empty because b dash x epsilon intersection E is a subset of bx r intersection E, but this is equal to x1 to xn. You understand that? Yeah, right. But none of these elements x1, x2, xn can be here. because the distance between x1 any xi here and x is less than epsilon, but epsilon is less than this. Okay, if you want strictly less than, take it strictly less than if you are comfortable. Maybe make it half of that. Okay, are you following? Okay, therefore the above thing is clear. Okay, please pause, review, proceed. Now I want to say 3 implies 4. What is 3? Every sequence has a convergent subsequence in X. Okay, then I want to prove X is complete and X is totally bounded. Okay, right. X is complete is easy because suppose Xn is Cauchy in X, right? By our hypothesis 3, every sequence has a convergent subsequence. That means there exists a Xn K, a subsequence of Xn which converge to some point X in X. But this is a well-known fact. Whenever I have Cauchy sequence Xn, and if I have convergent subsequence Xn K, then Xn will converge to X. Okay, this implies Xn converge to X. Therefore, every Cauchy sequence is convergent. Okay, I hope you would have seen it in real analysis. The same proof works in metric spaces. What is the thing? This is if you want, this is a lemma. It's a standard fact. I have Cauchy sequence Xn in X, and X and K converge to X, a subsequence. Then the original sequence itself converges to X. Therefore, X is complete. I have to prove X is totally bounded. Okay, that is also easy. Suppose X is not totally bounded. What does that mean? If it is totally bounded, it says for every epsilon positive, there exists an epsilon net. Remember, epsilon nets by definition are finite. If it is false, that means there exists an epsilon positive such that there does not exist any epsilon net. You understand that? Okay. Keep that in mind because this logic is something which you have to be careful about. So let's start with x1. So we are assuming x is not totally bounded, therefore there exists some epsilon positive so that there exists no epsilon net. You understood? Now choose x1 and x to be arbitrary. Now let's look at bx1 epsilon. Can this be equal to x? This is a subset of x, but can it be equal to x? No, because if it is equal to x, then x has an epsilon net, namely consisting of only one point in the net x1. So therefore this is not true. Right? You understood this? Okay. That means there is an x2 in x so that x2 is not in bx1 epsilon. Right? Very good. Now let's look at the union of bx1 epsilon union bx2 epsilon. Can it be equal to x? Again, it cannot because I have an epsilon net consisting of only 2 points x1 and x2. Therefore, this is also not true. This x is different from this not. Okay, this cannot happen. Okay, right. Okay, now I can prove by induction. Okay, there exists xn. Okay, which is not in b x1 epsilon union etc. b xn minus 1 epsilon. Therefore, by induction, I have constructed a sequence xn. What property? When n is not equal to m, distance between xn and xm is greater than epsilon, greater than or equal to epsilon. Do you understand this? Because xn is not here, that means xn, you understood that. Suppose n is not equal to m, without loss of generality, let us assume xn. That means xn not here, but your m must be between 1 and m minus 1. Therefore, it will be somewhere here. You understand that? B x1 epsilon union B xm epsilon union B xn minus 1 epsilon. Okay. So it's not here. That means the distance between x and xm is also greater than or equal to epsilon. Okay. I'm going through this kind of proof because many students just like that would like to accept it, but you should know how to prove it. Okay. Very good. Now there is a problem. What is the problem? Now I have a sequence xn in ex such that distance between any two distinct terms is greater than or equal to epsilon. Therefore, this means this sequence cannot have a convergent subsequence. Yeah, do you understand why? If it has a convergence subsequence, let us say x and k, and assume x and k converge to x, then I have a problem. Take, let us say, epsilon by 3, okay? Then for k very large and r also very large, then what is the distance between x and k, x and r? This will be less than or equal to distance between x and kx plus distance between x and r, x. But each one of them will be less than epsilon by 3. That is equal to 2 epsilon by 3. But I know this distance is greater than or equal to epsilon, right? But what I say, by triangle inequality, I get the distance is less than 2 epsilon by 3. That's a contradiction. Yeah, if you want for k greater than or equal to k naught. Okay, since it converges for epsilon by 3, there is a k naught, so that whenever k is greater than or equal to k naught, r is greater than or equal to k naught, distance between x and k and s, x is less than epsilon by 3, distance between x and r and x is less than epsilon by 3. Use that, then I get a contradiction. Yeah, very good. Okay, so what I have shown now, 3 implies 4. X must be complete. I have also shown that x is totally bounded. Right? Okay, next. Next, we have to say 4 implies 1. What is 4? 4 says if x is totally bounded and complete, I want to show x is compact. Okay. Okay. So let us assume x is not compact. Okay. The proof is the way you prove Heine-Borel theorem using nested interval argument. Nested interval theorem. Okay. See my article on nested interval theorem by me and its application. Okay, you will see that proof. I am just going through that proof. Maybe I can explain the proof quickly so that you will appreciate this. Yeah, I think I have time, so let me do that. Suppose I have closed and bounded interval AB. I want to show it's compact subset of R. Right. So the trick is, I'll just explain that strategy. I will not go into complete proof. Once you understand, you will see I'm going to mimic the same kind of argument here. Okay, this is a digression. Right. Suppose this is not compact. That means there exists an open cover which has no finite subcover, right? The trick is you bisect it. Now I have two intervals J1 and J2. This is J1 and J2, right? Let us call it J1. Now what do I do? So UI is also collection for J1 and UI is also an open cover for J2. So I claim one of them cannot admit a finite subcover, because if each one of them admit a finite subcover, their union will be a finite subcover for J. You understand? So choose one and call that as a J1. J1 does not have a finite subcover. I will call it a rogue. Okay. Now what do I do? Suppose J1 is this rogue. Now again divide it. Then there are two subintervals. See, one of the, so this collection UI is an open cover for this subinterval as well as for this subinterval. If I claim one of them has no finite subcover, because if they each one of them have finite subcover, then their union will be a finite subcover for this rogue. That's a contradiction. Therefore, one of them, right? So call that as a J2. Maybe both of them do not admit finite subcover, but choose one of them. So call it rogue. You understood this? Now, you find something very interesting. So by induction, I'll have Jn, so that Jn is a subset of Jn minus 1. These are all, each one of them is a closed and bounded subinterval, and each one of them is a rogue. And you can also see their lengths decrease by half each time. Therefore, their lengths go to 0. Therefore, by Nernst-Rauel theorem, there is a point common to all of them. Okay, and then use it to arrive at a contradiction. Okay, how will you arrive at a contradiction? Again, it's the same argument. Suppose x belongs to the intersection Jn, right? Okay. That means x belongs to Jn for every n. Now notice that x is an element of AB. Therefore, there is a J such that x belongs to Uj. You understand this? Very good. Now x belongs to Uj, but Uj is open. That means there exists an epsilon so that x minus epsilon to x plus epsilon is contained in Uj. Do you agree with that? Okay. But remember, x belongs to Jn. Therefore, Jn is some interval. Okay. This is my Jn. And x may be somewhere here, there. Right. Now notice the distance between any point y and x here. Right. That will be less than the diameter of Jn, which is the length of Jn, which goes to 0. Therefore, if n is very, very large, then Jn must be a subset of x minus epsilon to x plus epsilon. So fix one such n, then call it Jn, that is a subset of x minus epsilon to x plus epsilon. What is the contradiction? This Jn is contained in Uj. That means I have found a finite subcover, namely one single open set, a cover consisting of one single open set Uj, which contains Jn. But remember, Jn is a rogue, so that cannot happen. So this contradiction shows this must be compact. The same proof is what I want to do. Okay, please review this proof. It will make your life easy. In the general case, you will follow it much more easily now. Right. So what do I do? So what is given to me? X is supposed to be complete and totally bounded. I want to know whether it is compact. Is that right? This is what 4 implies 1. Let us make sure I am not goofing. Yeah. So as I argued earlier, okay, assume X is not compact. Suppose false. Then there is an open cover Ui, okay, which has no finite subcover. Okay, so I have to arrive at a contradiction like the way I did in the Hairy-Borel theorem for compact intervals, closed and bound intervals. Okay, how do I do that? See, here I bisected, right? Now I have to replace it. I have to find a subset which whose diameter keeps shrinking. Okay, therefore I have a convergence subsequent. That's a basic idea. Okay, how do I get that? That is where the total boundedness comes. So how am I going to use? So let us say epsilon equal to 1 by k, right? Where k is a natural number, right? Now remember, x is totally bounded. Therefore, for this epsilon, there exists an epsilon net. That means there is a finite subset of k of x. This is a finite set. So that what happens? X is union of b x 1 by k and x in fk. You understand this? Because this is because of total boundedness. X is totally bounded. Okay, this is the way this is going to replace our bisection trick here. So how do I do that? Let us look at. Okay, now remember x is contained equal to union ui and it has a no finite subcover. Now this x is union of b x1 x varies over f1. You understand? Right. Now this is a finite thing, right? So I claim there is at least one x in f1 such that bx1 has no finite subcover. At least one x in f1 so that bx1 has no finite subcover. Because if each for each x in F1 it has a finite subcover. Remember, x varies over F1, which is a finite set. Therefore, I have a finite covering for their union, and hence for x. That's a contradiction. You see that? That proves exactly what we did with the bisection trick. Yeah. So so call this x1 as a rogue element. Okay. So this x, let me call it as x1. So there exists x1 in F1 so that B x11 has no finite subcover. Okay. So I can, right? But I would like closed and bounded there. I would like to be closed also. So what I can do is I can rewrite this whole thing like this: B x1 x in F1. These are closed ball. My notation for closed ball is Bx R closed. This means set of all y so that less than or equal to R. Okay. This is my notation for closed ball. Okay. You understand? This is also equal to x. And this is also contained in ui. Therefore, there is at least one. So I can write it as the closed ball. Are you following me? Pause, review, proceed. If you are having difficulty, please go ahead. What is happening? It is always producing a next one. Ah, these are the kind of stupid problems with this. Okay, right? Okay. Now what do I do? Now I replace this x argument. Notice that earlier I replaced the argument by j for j1 as a rogue. Now I consider j1. Similarly, I am going to consider on bx1. Okay. Now let us look at bx 1 by 2. Okay. Okay. Now I know this is equal to bx 1 by 2 as x varies over f2, because this f2 is the epsilon curve for epsilon equal to half. You understand that? Therefore, this is an open cover for this. You understand? Yeah. Therefore, b closed interval x1 1 intersection x, which is bx1. Okay. Right, is equal to union b x1 1 intersection b x half, where x is in f2. You understand this? Okay. Now, okay. Now my ui is an open cover for x. Therefore, ui is an open cover for this. Okay. And how many are them are there? Finitely many. Therefore, I can write this as actually equal to this one, like last time. Okay. Are you happy? Sure. Okay. So there is at least one x2 in f2, so that b x11 intersection b x2 half has no finite subcore. These are rogue. You understand that? If each one of them, these are finitely many, as x varies over f2, each one of them has a finite subcover, then their finite union will have a finite subcover. That means bx11 will have a finite subcover. That's a contradiction. We are not concentrating on x now. Do you understand that? Our bx1 is a rogue. So that will be violated. Are you following? Therefore, this has no finite subcover. So let me call this as k2. Okay, this is as k1. Okay. Now I want to prove by induction. What will I do? Now I will try to, now first notice that. Now what do I know about k2? K2 is a subset of Bx2 by 2, right? Therefore, what will be the diameter of K2? Is at most the diameter of this, which will be less than or equal to 1. That is 2 to the power minus 1 times 2. You understand? Therefore, by induction, what will I do? I take K2. Now, what do I do? Now, let me show K F3. So, I will do that. Now, K2 equal to K2 intersection X, but that's equal to union X in F3 K2 intersection Bx 1 by 3. Do you understand this? Yeah. Therefore, what do I know? There is at least one x3 in F3 so that K2 intersection Bx3 1 by 3 is a rogue. Because each one of them is not a rogue, that would mean this being a finite union, K2 is not a rogue. But that's a contradiction because by our choice, K2 is a rogue. Do you follow that? Okay. Therefore, what do you think I have done? So by induction, I have a sequence Kn. Now, what is the diameter of K2? So call this as K3. What is the diameter of K3? See, K3 is contained in this, therefore it will be less than or equal to twice by 3. You understood? So whatever is the radius, you have to multiply by 2. That's the maximum radius, maximum diameter possible. Diameter will be less than or equal to that. It may not be equal to, right? If I have a ball, open ball of this, diameter of this ball will be less than or equal to 2r. Equality may not hold. Okay? Right. Anyway, you follow that. So by induction, I do that. How do I do that? I look at Kn minus 1 and you, okay, I intersect this with union of B x 1 by n, where x varies over Fn. Right? This is my Kn minus 1. Okay, now Ui is an open cover for this. Right? Ui is an open cover for this. So I say that one of these fellows, this is equal to union Kn minus 1 intersection B of x 1 by n in n Fn. See, one of these fellows is a rogue. If all of them is not a rogue, okay, but that union is Kn minus 1, that will be a rogue. You understand? Therefore, there is at least one xn in Fn, so that this is Kn minus 1 intersection B xn 1 by n is a rogue. Yeah. So I call this as Kn. And what is the diameter of Kn? That is a subset of this, therefore it will be less than or equal to 2 by n. Do you understand this? So I have Kn is a nested sequence, okay, so the diameter of Kn converges to 0. Right? Now notice that there is no nested interval theorem here. Last time I used nested interval theorem, but I have to be careful here. Now what will I do? Remember, so far I used in the hypothesis 4, x is totally bounded. There is another part of the hypothesis. What is that? X is complete. To exploit that, what do I need? I need a Quotient sequence. Where do I find a Quotient sequence? Well, you have given me Kn is n and diameter of Kn is going to 0. Therefore, choose yn and Kn arbitrary. I don't care what it is. Yeah. Then, if n is greater than or equal to m, remember that my yn and ym are in Km because this is a nested sequence. This is nested by our construction, right? And therefore, what is the distance between yn and ym? That will be at most diameter of Km. That is 2 by m. Do you follow that? Therefore, if n is greater than or equal to m, yn and ym both are in Km. Therefore, distance between yn and ym will be less than or equal to diameter of Km, which is less than or equal to 2 by m. That goes to 0 as m goes to infinity. You understand? Therefore, yn is Cauchy. Right? Now I can make use of the hypothesis. What do I know about X? X is complete. Therefore, there exists a Y in X so that yn converges to Y. Okay. Now the argument is exactly like Henry-Borel theorem argument, which I just said that. Now this Y belongs to X and X is union of Ui. Therefore, there is a J so that Y belongs to Uj. Right. Now Uj is open. Therefore, there is an R so that BYR is completely contained in Uj. Right. Now Y belongs to Kn for each n. Why? That is because look at that Y, let me say YR, R greater than or equal to N. This is a sequence in where? In Kn. And what do I know about Kn? Kn are closed. Go back to the way we did. What did we take? Kn minus 1 intersection closed ball Bx1. Both are closed sets. Therefore, the intersection is a closed set. Therefore, my Yn, Yr, R greater than or equal to N is a sequence in Kn. And since Yn converges to Y, Yr converges to Y. Since Kn are closed, that implies Y belong to Kn for each n. Do you understand this? Pause, review, proceed. Therefore, Yn belong to Kn for each n. Now there is a problem. What is the problem? Since the diameter of Kn is less than or equal to 2 by n, right? If I choose n sufficiently large so that 2 by n is less than r, then what do I know about Kn? See, Y belong to Kn, K capital N, and let Z belong to capital Kn. Then distance between Y and Z is less than or equal to 2 by n, but that less than r. That means Z is in BYR, but BYR is contained in UJ, but Z is arbitrary point of Kn. Therefore, Kn is contained in BYR, that is contained in UJ. That means Kn is not a rogue. But this contradiction actually makes us happy, right? You understood that argument? Okay. So what I have shown now? I have shown that the X, our assumption that X is not compact is false. Okay. There's if unless your metric space ideas are very clear, you will struggle to understand, but it's worth going through. And if you want to master, I would suggest please go through my topology of metric spaces. It has lot of good exercises and examples which will make you confident, so that this kind of proof you will find it much easier. You think that I unnecessarily explained too much. Okay, right. Okay, that completes the proof. I hope all of you are happy. Happy? Okay. Now my promised thing. See, now we have proved all these four conditions are equivalent for a metric space to be compact. Okay, good, very good. Now, as I said, the first condition one, the first characterization, that's a typical of general topology. Many people are kind of fond of that. But as I said in analysis, okay, analysis always means estimate. So you have to do something with sequence, infinite process, something. So what are the things which are very important for analysis? I will tell you. 3 and 4 are the most important characterizations if you want to do analysis. Whenever you have metric space and compactness, 3 and 4. And again, let me tell you what are the advantages. Okay. When you want very highly abstract theoretical results, 4 may be easy. That is, to show something is compact, you will show it is totally bounded and complete. Okay, for example, you can look at a proof of Arzela-Ascali. Okay, either in my book or in one of the videos. I think in the fourth video of Arzela-Ascali, I proved Arzela-Ascali theorem by the fourth characterization. Okay, but for many easy problems, 3 will be easy. It's a handy tool. I'll just stop, give an typical application and stop the lecture at that. Suppose all of you know this. Suppose I have F. Okay, suppose XD is a compact metric space and it goes to real number. Assume this is a continuous function. So I want to say, let us say F is bounded, and since if it's bounded, then I can talk about LUB of Fx as x varies over capital X. Okay, since the bounded set, the LUB exists in real numbers, call it alpha, call it M. Then we know that there is an x in X such that Fx equal to M. That is what you closely say. Yeah, any continuous function in a compact metric space attains its bounds. Right? Now I will give a proof. Suppose F is not bounded. Okay, then there exists for every n, there exists xn in X such that f of xn is greater than n. Bounded up, let me say bounded above, not bounded above. Similarly, bounded below you can prove. Or you can even use mod f. Okay. For each n, there exists xn such that mod f xn is greater than n. If not, there is an n such that for all x, mod fx is less than or equal to n. That means f is bounded. You understand? Therefore, f is not bounded means that. Now I have a sequence xn. So what do I know? By the third characterization, I think third characterization, right? Yeah. There exists x and k which converge to x in x. Right? Now f is continuous. Therefore, what do I know? Fs and k must converge to fx because of continuity. But that would mean fx and k, okay, this sequence must be bounded. But that's a contradiction because mod fx and k by our construction is greater than or equal to or greater than nk for each k. Remember, nk is greater than or equal to k for each k. Therefore, mod fx and k is greater than or equal to k for each k. Right? Therefore, if it converges, okay, this cannot be bounded. You understand? Right. Next. Okay. So I know, therefore I know the f is bounded. So let us look at if it's bounded, therefore it's bounded above as well as bounded below. Let us look at LUB of fx for x in m. Okay. I want to show there exists an x. Suppose there does not exist. Okay. I want to claim there exists an x inside that this happens. Yeah. Okay. Now we have to arrive at a contradiction. Yeah. Let us look at f. M minus 1 by n. This is strictly less than m. This is the LUB. Therefore, this is not an upper bound for the set. That means there exists xn such that f of xn is greater than m minus 1 by n for each n. Do you agree with that? Yes or no? Okay. Sure? Because this is not an upper bound. Therefore, there is an a such that fxn is greater than m minus 1 by n. Okay. Because most of the problem with students is the LUB, supremum, etc. They have to be thorough. Then only you will follow. Okay. Anyway, this is all right. Now I have a sequence xn. Therefore, there is a sequence xn k which converges to x. Therefore, my fx and k must converge to fx. Yeah? Do you understand? Right. Now, let us understand something about thing. What do I know about x and k? Minus 1 by nk is less than f of x and k, but that is less than or equal to m. Now, notice that this converges to m. This converges to m. Right? And if at all this sequence, then this sequence must converge to m by sandwich lemma. But then xn can converge to x by continuity f of xn can converge to fx. Therefore, this also converges to fx. But uniqueness of the limit therefore shows fx equal to m. You see, that's a proof. Okay. I hope you enjoyed. Go through. Yeah. Please go through the proof. This is the simplest proof, in my opinion. Go through twice or thrice. You'll that will also give you confidence how to work with a lot of concepts from metric spaces. Yeah. I hope you enjoyed it. We will meet again sometime.